In this video, we will learn the most important points about the Fourier transform and the inverse Fourier transform of discrete time signals. In the first part of the problem, we are given x e to the power of j omega and we are asked to find xn. To solve this, we first need to review a few important points. The first point is that the Fourier transform of a to the power n multiplied un is equal to 1 divided by 1 minus a e to the power minus j omega. The second point is that if the Fourier transform of xn is x e to the power j omega, then the Fourier transform of x minus n will be x e to the power minus j omega. This property is called the time reversal property. The third point is that if the Fourier transform of xn is x e to the power j omega, then according to the time shifting property, the Fourier transform of x n minus n0 will be e to the power minus j omega n0 multiplied by x e to the power j omega. Now, to solve this problem, we first need to decompose the Fourier transform into simpler fractions. There are different methods for partial fraction decomposition, and here I will directly write the final results. Using partial fraction decomposition, we can write x e to the power j omega as the sum of two terms. Now we need to find the inverse Fourier transform of these two terms and then add them together to obtain the final result. According to the first point, the inverse Fourier transform of the first term is a to the power n multiplied by un. To find the inverse Fourier transform of the second term, we proceed as follows. First, using the first and second properties, we note that the Fourier transform of a to the power minus n multiplied by u minus n is equal to 1 divided by 1 minus a e to the power j omega. Now, using the time shifting property, if we choose n0 equal to minus 1, then a to the power minus n plus 1 multiplied by u minus n plus 1 corresponds to 1 divided by 1 minus a e to the power j omega multiplied by e to the power j omega. Because n0 is minus 1 and therefore e to the power minus j omega n0 becomes e to the power j omega. Next, we rewrite a to the power minus n plus 1 as a to the power minus 1 multiplied by a to the power minus n. Since a to the power minus 1 is just a constant coefficient, we can move it to the other side. As a result, the inverse Fourier transform of the second term becomes a to the power minus n multiplied by u minus n minus 1. Now, if we add the inverse Fourier transform of this first and the second terms together, we obtain xn equal a to the power n un plus a to the power minus n u minus n minus 1. In the second part of the problem, we are asked to compute a certain integral. To do this, we first recall that using the inverse Fourier transform formula, we can write xn as follows. To evaluate this integral, we first rewrite it as x e to the power j omega multiplied by 1/2 times e to the power j omega plus 1/2 times e to the power minus j omega times 1 divided by 2p. Here we use Euler formula which we discussed in previous videos. Next, we split this expression into two separate integrals. If we compare the first integral with the standard inverse Fourier transform relationship, we see that n equals 1. Similarly, by comparing the second integral, we find that n equals minus 1. Therefore, the first integral corresponds to x at 1 and the second integral corresponds to x at minus 1. So the result can be written as 1/2 times x1 plus x minus 1. From the previous part, we already found that xn is given as follows. Now we simply substitute n equals 1 and n equals minus 1. When n equals 1, we obtain x1 equals a because the unit step at minus 2 is 0. When n equals minus 1, we also obtain x minus 1 equals a because the unit step at 0 is equal to 1. Finally, the result becomes 1/2 times a plus a, which is simply a. This video was about the Fourier transform and inverse Fourier transform of discrete time signals. We have also discussed related topics in other videos on this channel. If you are interested, you can follow our channel and watch those videos as well.